So mathematical quantity with direction and magnitude, and we usually denote it with a line segment that has a starting point and an ending point. And in general, we want to be kind of bold point, the starting point, and then we put an arrow on the ending point. So this is our usual drawing of a vector. We want to point out that the x and y, or the x, y, z value point here is sometimes called the head of the vector. And then where it starts is sometimes called the tail. Yeah, Fernando. Not quite. Velocity, yeah, velocity could be a vector, but velocity doesn't necessarily have to be a vector. And also there's other vectors that that exist that are not velocity. Okay, so we have a head and a tail of a vector, and we could do things with these vectors. So the main definition for a vector is that it's something with a direction and magnitude. So if I see another vector, with a different direction and magnitude, then those two vectors will be different. But if I see another vector with the same direction and the same magnitude, even if it's a different color, it's still going to be the same vector. Magnitude, the direction. The direction is going to be which way it's pointing, right? We can define that by drawing a horizontal to give us a lift. That we could do that in 2 dimensions, but in 3 dimensions it gets a little trickier. But we can still find the direction by the way it's pointing. And the magnitude, what's the magnitude? The magnitude is the length of the vector. So the direction, I don't want to say it's just intuitively drawing whichever direction is, but I guess let's focus a little bit more on the magnitude. So the magnitude is the length of that directed line segment. Danny?
Do you ever talk about pseudovectors here?
Nope.
Okay.
What are pseudovectors?
It's just a way to, I don't know much about it. I know it's later in physics.
Oh.
It's just another way to look at vectors in three-dimensional space.
Yeah.
Yeah, pretty crazy.
We'll definitely look at vectors in 3D space, but I don't call them pseudovectors, and maybe they have other special properties that I don't know of. Okay. No, we're not going to do that in this class. Okay, so we could label vectors as whatever they might be, whatever you might want to label them, like A, B, C, or V. Usually they start V with vectors, because vector starts with a V. But what's important is that if it's a vector, then we want to denote it with something else, and that would be an arrow on top of the symbol to denote this as a vector. Now, in books, most books, they use a bold notation for vector, but when you're writing the vector and you want to boldface it, you know, when you're writing fast, you don't want to just stop on the letter and just make sure that it looks like it's boldfaced. And so the arrow on top would be the key to writing a vector. Sometimes physics people use hats. I think it's going to be the same idea. Oh, a hat is for a unit vector? Okay.
Yeah.
Whatever they do on the physics. Yeah, it looks like the carrot that's sitting on top. Yeah, so we'll talk about the unit vectors and standard unit basis vectors, as they call them. Yeah.
And in physics, the axes are labeled differently than
No, I
I'm
don't.
pretty sure it is. It's like,
Yeah, it's just different. It's like X or Y is up, down, X is left, right, and Z is forward, backwards for
Oh.
physics, but in math it's Z is up, down.
Yeah.
X is left, right, left.
Okay. So I don't know why they do it that way. In computer science, they do it even differently, even because they have one of them goes down because they're looking at the screen. The top left is like the origin. So they do a lot of weird things. But in math and physics, regardless of how you look at the vector, it still has to follow the right-hand rule. And in computer science, it kind of loses that idea because the y goes down. Anyways, so we can name these vectors with letters like V and W or A and B, and as long as you put the arrow on top, then it would be denoted as vector. And we can see that the red vector and the blue vector here are equal, although they're not at the exact same spot. The criteria for a vector is a direction and magnitude, and as long as the direction is the same and the magnitude is the same, then it's the same vector. So in this case, we can say that V, vector V, is actually equal to the vector W. Because it has the same direction and magnitude. And then we can call this other vector, kind of run out of names after V and W. What comes after W? X. X, Y, and Z, we kind of have reserved that. So sometimes people start with A, B, C with vectors, but sometimes A, B, C's are numbers. So that kind of brings us to the definition of a scalar. And it's funny because a scalar is something that we've been working with all our lives. Whenever we think of a number, well, that's just a number. But that's what a scalar is now. So now that we have a vector, we're going to use the word scalar to represent a number. Okay? So whenever we hear the word scalar, think about that as just a real number. And Joe was asking earlier about R2 and R3 and stuff like that. So let's
Instead of full bars, just all real numbers.
yeah. So let's just talk about the notation that I use when I handwrite and most people use, and that's an R with like the double-sided, and this is the set of real numbers. And so they have R with an exponent 2, and usually I tell people if you have x to the exponent of 2, you say x to the second power or x squared. And when my algebra students say, oh, that's x2, I said, no, don't say x2, it's x to the second power or x squared. But with this notation R, you don't say r to the second power, you actually say R2. So R2 is going to be the set of ordered pairs and mathematically in set theory, when you would write this as a set, you would say x and y in parentheses, that's the ordered pair, such that x comma y, x and y are real numbers. And so what this is saying is that you're basically saying that you're talking about this as the xy plane. In some cases, in the future, we might refer to it as a UV plane or an ST plane, but that's just variables. It's just variable talk. So we can just switch variables as we need to, but in general, it's the XY plane. We know it as the XY plane. So we can rewrite everything over here, except instead of saying ordered pairs, we can say ordered triplets. Or in set notation, it's instead of x, y, and z, such that all these values of x, y, and z are real numbers, or the x, y, z space. And then the main thing about this is that we want to give it dimension. We're going to be talking about, we have been talking about 3D. So we want to be able to say, if we're talking about something in 2 dimensions, we can just say, oh, let's refer back to R2. Or if we want to talk about something in 3 dimensions, we can say, oh, let's refer back to R3 and take a look at that. And of course, in math, you can go higher dimensions like R4, R5, Rn, or anything really. And we can mathematically and abstractly think about those, but then physically now, we can't visualize that since we are only capable of visualizing up to 3 dimensions. So we can't visualize anything in 4 dimensions. Unless you're in an altered state of mind. Which is, apparently it's legal now here in California. Yeah?
Another, like, 4 dimension would be, like, 1 dimension would be considered time.
Yeah, I mean, we can always bring that up in physical terms if we want to stay with physics. But it doesn't always have to be time. It could be temperature. It could be any other variable you want to make it out to be. Think about a 4-dimensional idea would be the temperature at any point in this room. So a point in this room can be a 3-dimensional point, x, y, z. And then if you add on the temperature at this point exactly, then that's x, y, z, t. Now you have something in 4 dimensions.
Can you also have like concentration of like pH?
Oh yeah. So the pH in the air, I don't know if that would work in the air, but
like you have a fish tank,
yeah.
like looking at
So you can look at the space in the fish tank in 3 dimensions, and then each point in the fish tank will have some sort of pH measurement. So that would be x, y, z, pH, something in 4 dimensions. You can even throw the temperature in there. So x, y, z, t for temperature, pH. So that's a 5-dimensional vector now, or point, or vector. Vector or point, we'll talk about that in a minute. Danny?
Have you seen Interstellar?
No, I want to see that.
You should.
Yeah.
Talk about tesseract in there.
Yeah.
Like, it's pretty. I heard that physics is actually pretty accurate.
it gets a little wonky towards the end of the lead up of the
Yeah, it does.
It always gets wanky in the end
Yeah, always, but-
because it's all speculation, right? Yeah, there has to be some resolution in the movie. So, anyways, a scalar R is a scalar, or the set of all those values in R is a scalar. And when I say R2 and R3, I said points, but I want to try to argue with you that we should be able to interchange the idea of a point and a vector. When we have a point, we can think about that as a vector. When we have vector, you can think about that as a point. So let's see how we can do that. Let's take our v vector and take it with us. So let's talk about a vector. A vector is something with a direction and magnitude, right? We've kind of established that. And so let me try to make this argument in 2 dimensions, and imagine this could happen in 3 or 4 or 5 dimensions as well. So in R2, what we can do is we can bring this vector. The vector has a head and a tail. You guys are comfortable with the head and the tail now. It has a direction and a magnitude. And what we could do is we can bring this vector to have its tail be at the origin. So I'm going to draw the XYZ plane. And I'm going to move that vector so that its tail is at the origin. So now that I've done that, what I could do is I can look at the head. So I know for sure that the tail is at the origin because I put it there. And now the head is going to be pointing at some point in R2, right? So let's call it AB. I don't know what that, I mean, it could be, 5, 3 or whatever. So it's just some point AB, where A and B are real numbers. So it turns out that we can write V as a vector. Now, the vector can be written in a few different ways. The textbook and the homework asks you to make sure that if you want to express a variable as a vector, that you put an arrow on top. And then if you're going to write components for the vector, that you do one of 2 things. One is to use these brackets, alligator brackets, greater than, less than brackets. But I don't think you just hit the greater than or less than sign in your homework. You have to actually look at vectors. When you put your thing on, there's
you can do just alligator brackets.
Oh yeah, like greater than, less than.
Yeah, I've been working at it.
Okay, awesome. So one way to denote vectors is with these alligator brackets, to say that a vector whose tail is at the origin and head is going to be pointing at the point AB, you can write that vector as A comma B. This, by the way, is a vector in standard position. And so a vector is in standard position if the tail is at the origin. Is it at the origin or on the origin? Let's use at. I think at is better. It's positioning, right? So if the tail's at the origin, then we say that the vector's in standard position. And if vector's in standard position, you can call that vector by name now, AB, whatever point the head is pointing to, wherever the head's at. So that is when we can consider the point as a vector and the vector as a point. So the point AB is essentially equivalent to the vector AB. So that's just the notation that I'll be using in class. I'll try to use the vector notation, but in case my alligator bracket starts turning into parentheses, then we know it's all the same thing, right? It's just that in the homework you have to be careful to actually use the alligator brackets to denote vectors. And so, are you talking about this? can't parse this. Hello? I just figured I keep writing like this, and eventually by the end of class you'll figure out what I'm writing. It's your job as students, right, to try to figure out, decipher. You have to decipher the instructor's accent, and then eventually decipher their writing, and decipher how they grade. So.
You wondered how we don't have like massive number of deaths when like the people who fill out prescriptions have to read the doctor's handwriting.
Doctors, yeah. Yeah, so we could say that there must be some doctor that has worse handwriting than I do. There might be some instructors that have worse handwritings than I do. Probably not. No? Thanks, Tommy. All right. This, by the way, when you bring a vector in standard position and then you find out the point that the head points at, this is called resolving a vector. So some of the questions that they might ask you in homework or in the book ask you to resolve a vector, or they say this is how you resolve a vector. So this whole process is resolving a vector. So resolve. Yeah, I didn't take it out yet. Did anybody start 10.6? If somebody started it, then I might not be able to take it out. So we'll see. Yeah, maybe. So the whole idea behind resolving a vector is that you have the vector, this red vector that used to be out in space somewhere. If somehow you can bring that to the origin and figure out the point components in standard position, then you've resolved the vectors. So sometimes you might see a picture of a vector, or sometimes they might give you some information about the vector. They might give you the direction with respect to some angle from the horizontal or something like that, and then they can give you the magnitude. And so if they give you that information, then you should be able to, quote, resolve the vector. Yeah, that looks like an S, doesn't it? 8. S. Standard position. All right, let's talk about adding, subtracting, and all kinds of other stuff that we can do with vectors. So let's take a look at this from a visual point of view first, and let's draw a couple of vectors. Let's call this vector V and W. So we're curious about what V plus W might look like. So with vectors, what we could do is we could take a look at V and take W and draw the vector so that the head of V and the tail of W, the W is what you're adding, would be the same point. And we can have this in standard position. We can have like V in standard position, or we can just have it anywhere in space if we just want to basically take a look at how the vectors might look like. So to find the sum, you would start with the vector V, the tail of vector V, and you would go to the head of vector v, but then you take that, take w, and go to the head of vector w, short. So from head to tail, this is your new vector v plus w. Notice that addition is commutative, so instead of starting with w, or instead of starting with v like we did, we could actually start with w first and then add v to it. And we should still get the same point, or the same vector. We should still end up the same vector. So it turns out that v plus w is exactly the same as w plus v, arrow. Yeah?
We are pretty resultant vectors in this class, or
Say it again?
resultant vectors, or something?
Yeah, the resultant vectors.
Okay.
I would just say the result.
Okay.
So when you add two vectors, you're going to get a vector, and the vector, if you make a parallelogram out of v and w, it turns out that that parallelogram has a diagonal, and one of the diagonals is the sum of the two vectors. So now let's take a look at v minus w. It turns out that v minus w, what I'll do for that one is I'll put v and w kind of back to each other. And v minus w is going to be a new vector that is going to have v and w as the head and the tail. Now, which one do you think should be the head and which one should be the tail? V is the backwards. First one's. So whenever we think about making a vector, let's think about head minus tail. And so if we kind of say that, head minus tail, then it kind of gets our subtraction figured out. So the tail is going to be w, that's the green vector, and the head is going to be v, that's the purple vector. Falling short again. So this is v minus w. And w minus v would just be the same vector except going the other way. Yeah, Frederick? Yeah, but I forgot to talk about scalar multiplication, which is what I'm going to talk about next. Yeah, I ran through that in my head, scalar multiplication. Haven't done that yet, so let me think about it this way. Just head minus tail. And this would be good for later on. You might want to connect 2 points together with a vector, and if it does matter which way you're going, then think about the head minus tail. There are going to be some times where it doesn't matter which way it's going, because there's some times with the vector work, the direction doesn't matter. And if that's the case, it doesn't matter which one the head and which one the tail is. But when it does matter, then you want to make sure you put the head first ahead in the subtraction. Now let's take a look at one more idea with some basic. By the way, this is the other diagonal, if you didn't notice already. The other diagonal from the parallelogram, right? So the addition and subtraction turns out to be the diagonals in the parallelogram that you'd make out of the two vectors. And by the way, this will work in 3 dimensions as well. The way we're talking about it, works in 3D. And the last thing, or the next thing I want to talk about is the idea of a scalar multiplication. What's a scalar again? It's a number. A number, not a vector. So a scalar multiplication takes a vector and multiplies it by a scalar. Maybe we might need more room here. So let's pick a scalar like 2. 2 is usually a nice scalar. 1's a nice scalar, but it's kind of boring. So let's take a scalar. And we start off with our vector v. Pen, purple, v. And now let's multiply this vector v by a scalar 2. And what happens when you do that is that you kind of essentially double it. What are you essentially doing to this vector? You're adding another one, you're doubling it. Is there another word for that? No. No. I mean, all those are kind of correct, but that's not exactly what I was looking for. You're scaling it. Scalar multiplication. Right? You're scaling the vector. You're doubling it. Or you could take half of it if you want. Hell, you can even take the negative of it. And so Frederick made a comment about the minus, head minus tail business. That would have made a little bit more sense if I had talked about scalar multiplication first. So we'll talk about, let's do a couple more examples where we're cutting it in half. Like 1/2 v. So 1/2 v is essentially taking this, going in the same direction, except the magnitude now has been cut in half, has been scaled, so to speak. I'm not getting the tips of my points correctly. How am I going to flip it over? So when you multiply, when you scale a vector by a negative number, you're essentially making it go the other way. So the direction changes. If you multiply it by -1, the direction will change, but it'll remain the same length. But if you multiply it by -2, the direction will change, and it would scale to 2, twice as long. Okay, so here are the sample scalar multiplications that we can do. And then if you combine this whole idea of the subtraction, which is what we do in algebra. I mean, by the time people get to algebra, people know how to subtract. But subtraction is really adding the opposite. So we can think about that in vector terms as well. So the v minus w problem that we were looking at, is here. So we can imagine this as going from v. V is the purple vector. Go a little higher here. V is a purple vector, and then I'll take w and turn that around, how did I turn it around last time? I just rotated it. And then so now I'm adding v plus negative w, so I'll take the negative w and put it over here. So I have my v, and then this is now negative w. And then if I look at that, to see where it starts and ends, didn't quite land perfectly, but you get the picture. Turns out that this is these two are the same vectors, except the other vector, we saw it over here, right? But as long as it has the same magnitude and same direction, then it's the same vector. So, yeah. Yes, that's another section. Okay. This is the geometry of it. Algebraically, what we want to do is we can look at examples of vectors and then see how they would react if you add, subtract, and multiply them. And as you'll see in the next couple of examples, it seems obvious or natural. So let's try to look at this from an algebraic point of view. So let's start off with some vectors again, and let's give it some values. And we can extend this to higher dimensions, but we'll just take a look at it in 2 dimensions. So the idea of v plus w is addition, and then we can write down the resolved vectors that we have. And the way we would do this is literally just adding component by component. So it would be 1 plus negative 2, comma 2 plus 3. And that would give us a negative 1, comma 5. We can subtract the same way. V minus w, 1, comma 2, plus or minus negative 2, comma 3. So this will give us in the first component 1 minus negative 2, 2 minus 3. So this will give us a 1, comma 0. No, negative 1. The first one? 3. 3, comma negative 1. Careful when you subtract. And then a scalar multiplication, 5 times v, for example, would be 5 times 1, comma 2. And this would just be the 5 being distributed component-wise. 5 times 1, comma 5 times 2, which is 5, comma 10. Okay? It's as obvious as what you would think it would do. All right? So one more idea. Yeah, did I do something wrong?
Vector b plus vector w, we have that negative 2 at the top, but it's suddenly a positive 2 down below.
Oh, this 2 came from here, maybe?
Yeah, I think you want, because it would be negative 1, it'd be negative 1, comma 5. Yeah,
Yeah.
it is, but I'm looking at the,
Is that right?
oh, never mind.
Okay. All right. So one more idea. I'm going to a new page. You guys look like you're copying stuff. Onto the new page. Sorry for those people that were copying. Let's draw that vector again, some random vector. It turns out that there's special vectors in R2 and R3. And in R2, there's two special vectors that we sometimes call as the basis vectors. And these are supposed to be the same size, but different directions. And these are the, is it longer now? These are called the standard unit vectors. 1, 2, 3, 4, 1, 2, 3. Let's just say that they're the right size. So let's say this vector that I have here is a vector whose in standard position is 1, 2, 3, 4, 4, 3. So we can call that vector with brackets 4, 3. But then if we define these special vectors called the I, J, standard unit vectors, standard unit vectors. So hat, because they're unit vectors and they form a basis. Basis, if you're taking linear algebra, or when you take linear algebra, you'll learn more about basis vectors. Then these are the vectors that can represent I, for example, is equal to 1, 0, and J is 0, 1. So if we can represent the red vector 4, 3 as a linear combination of these standard unit vectors, that's our fancy linear algebra talk. If we can write it as a linear combination of this, then we can write the vector, any vector, as a linear combination of i's and j's. So what that means is that if I can scalar multiply I by 4, as long as the I direction in the y direction, as long as it goes in the y direction, maybe I'll change this a different color. So I have 4i, scalar multiplied that, and then I'll take the j vector and scalar multiply that by 3. And then I can imagine adding those two vectors. If I add those two vectors, I would get that little box or rectangle, right? And then I would start at the origin and end up at the head of this vector, so that's exactly the same. Yeah? Yes. So in exams and quizzes, I'm flexible as to how you guys write your vectors. So you can write it as a point with parentheses. I'm okay with that. Yeah. You can write it with the brackets like this. And now we've just found a linear combination of 4i, I, plus 3j, or 4i hat plus 3j hat, to be all the same thing. So you'll see that when you're dealing with vectors in WebAssign, I hat and j hat are also possible answers and responses to your questions. Okay? Now, in R3, you'd have a third unit vector called k. ij, that's the next one in the letter, right? I, j, k element. So the k vector goes in a z direction. And so your I and j will have one more component because it's in 3 dimensions, and then you would have a k component. Okay, so that's enough for you guys to think about for now. You guys should be up on the homework, and I'll try to delete 10.6 in the homework set.